We're now getting ready to move into fluid dynamics, and fluid dynamics is a very mathematical type of science. And to make sure that we all have a good understanding of the equations when they're written, I want to start off with a little review of some vector notation, because all of the equations of motion that we use will be written in vector notation as we move through this section of the course. I want to start off with the del operator. The del operator can operate on a scalar. It can be dot product with a vector, or it can be cross product with a vector. And the del operator is just the partial derivative with respect to x in the I hat direction, plus the partial derivative with respect to y in the j hat direction, and the partial derivative with respect to y in the k hat direction. What do I mean by I, j, and k? We're primarily going to be using Cartesian coordinates in the fluid dynamics part. And in the Cartesian coordinates, what you traditionally think of as the x direction is the positive I, the y direction is the positive j, and the vertical direction up is k. That would be the z direction. In atmospheric sciences, the I hat vector is going to be in the east-west plane. The j hat direction is going to be in the north-south plane, and the k hat direction is going to be in the up and down direction. So if we take this del operator and we apply it to a scalar, in this case temperature, you basically have to take each of the individual terms and operate it on that scalar. So that you just put the t in each one of the operations, and you'll end up with partial t over partial x in the I hat direction, plus partial t over partial y in the j, and partial t over partial z in the k hat direction. And we refer to this as the gradient. It's how does the temperature change in the east-west direction, how does the temperature change in the north-south direction, and how does temperature change in the vertical direction. And once again, we refer to that as the gradient. And that del operator can be applied to any scalar to get a gradient of that field. So for example, we could put pressure in here, and you would have a pressure gradient. If you wanted to put dew point in there, you could have a dew point gradient. You're not limited to anything other than the fact that that's the operator is being applied to a scalar. So the next thing we can do is we can do the dot product. And if you want to remember what the dot product is, basically the I hat dot the I hat is equal to 1, j hat dot j hat is equal to 1, and k hat dot k hat is equal to 1. All other combinations are essentially equal to 0. So in this case, we're going to do the dot product of the del operator and the velocity vector v. Velocity vector is dx by dt in the I hat direction, plus dy by dt in the j direction, and dz by dt in the k direction. And in atmospheric sciences, we're going to replace this dx by dt with the lowercase u. And so from now on, when I talk about the u wind, or the u component of the wind, what I'm talking about is the east-west component of the wind. Likewise, we're going to replace the dy by dt with the lowercase v. And so when I talk about the v component of the wind, I'm talking about the north-south component of the wind. And dz by dt is replaced by w. W is the vertical velocity. And the vertical velocity is typically an order of magnitude or more smaller than the horizontal velocity in the atmosphere. So we have this velocity vector, ui plus vj plus wk. And the del operator is being dot product with that velocity vector. So you take the first term and you dot product with the first term over here. And so you would apply partial over partial x to the u velocity, the u component of the velocity. And you get partial u over partial x, and the I hat dot product with the I hat gives you a value of 1. So I had to get rid of the vectors on there because it's no longer a vector. So I hat dot j hat for partial v over partial x. I dot j is equal to 0, so that term goes away. likewise, the I dot product with the K goes away as well. So from this first term, dot product with each of these, you only end up with that first term. So the second term, partial y, partial with respect to y, j dot I is 0, j dot j is 1, so we apply the partial v over partial y. Likewise, you can go through that and get partial w over partial z as well. And this is no longer a vector, this is now a scalar, and it's known as the divergence. So partial u over partial x. So that would be, how is the velocity of the wind changing in the east-west direction? I often think of this as being, as you're trying to get on the highway, all the cars are initially stopped, their velocity is equal to 0, and then the green light turns and people start to accelerate, and the velocity changes with distance, and as that velocity accelerates, you actually end up with a divergent situation. Conversely, when all the cars start slamming on their brakes, they all start coming in closer to one another, and that's a convergence situation. And this is a mathematical expression of that divergence and convergence, in this case, of the wind. And you can think that that might be important because if you have regions of convergence in the atmosphere, it's squeezing the atmosphere from the sides, and if that happens to be done near the ground, then the only way for that air to move is upwards. If you squeeze the air, have convergence in the aloft, above the surface, then air will move upwards above that and downwards below. So you squeeze it, it's got to go up and down from that region. So convergence and divergence are very important quantities to understand in the atmosphere. The third application of this is the cross product. So the del operator crossing with the velocity vector. The cross product, well, you have to use the right-hand rule. And we'll start off saying that the cross product of like vectors, I cross I and j cross j, I cross I, j cross j, and k cross k are all equal to 0. Otherwise, what we're going to do is we're going to use the right-hand rule. And you can't do this with your left hand, that's why they call it the right-hand rule. So in this case, I have the I hat vector, and I'm going to cross that into the j hat vector. So I cross j, my thumb tells me the resultant vector, which in this case is the positive k direction. So I cross j is equal to the k hat vector. Likewise, if I go I and then cross k, my thumb is now in the negative j direction. If I want to do j cross I, I'll be in the minus k direction. If I want to do j cross k, I'll be in the positive I direction. And if I do k cross I, I'll be in the positive j. And if I do k cross j, I'll be in the negative I. I don't have these memorized. If I'm trying to solve a problem, you'll always see me doing my right hand and crossing those vectors in order to get the resultant. So right hand rule, don't use the left, and remember that the cross product of the same vector is essentially 0. So let's go ahead and do that. So let's take the first term, and we're going to cross that with the first term over here. I cross I, 0. Doesn't have a resultant. So I cross j, the I cross j gives me the positive k, and so I apply that to partial v over partial x in the positive k direction. And then I'll apply the last term, the I cross k. The I cross k over here is in the minus j direction. So partial w over partial x is in the minus j direction. So that's you get two terms out of that first one, and then you do the same thing. J cross I, back to our little cheat sheet, j cross I is in the minus k direction. So that's going to be minus partial u over partial y. And you can continue on, so forth, until you get this expression. And we refer to this, and mathematics they often refer to it as the curl of the velocity vector. And what we refer to it in atmospheric sciences is the vorticity. Vorticity is the measure of the rotation of a fluid. So the first term here is the rotation of the fluid around the east-west direction. So east-west this direction, and this is the rotation around that. The second term is the rotation around the north-south vector, this direction. And the k-hat direction is the rotation in the vertical. And it's this vertical component of the vorticity which is extremely important for atmospheric sciences because you can think about the rotation of highs and low pressures. That's essentially a vorticity. You have rotation with inside a hurricane. We have very strong horizontal vorticity. And then we also have inside a tornado. We can have that very strong vorticity in the k-hat direction. And this is a mathematical way to describe the strength of that rotation. Another type of operator that we use in atmospheric sciences and a lot of scientific disciplines is the Laplacian operator. It looks like the Del operator, but it's not. It's got the squared up here. And it's an operator, the second derivative, the second partial derivative with respect to x, the second partial derivative with respect to y, and the second partial derivative with respect to z. And in this case, if we apply it to a scalar, say temperature, then you just put the temperature, you apply the operator, and you put temperature in each one of those, and you end up with this expression here. And once again, this is going to be a scalar. It's no longer a vector. In fact, it didn't start off as a vector, so anyway. So those are the operators that we use. And when we rewrite the equations of motion, they're going to be written in a lot of this type of notation. And this is shorthand notation that hides a lot, but I want you to be familiar enough to be able to expand all of these terms into all of their components. That's one of the very important things that we'll get out of this section is being able to expand these operators into their full components.